Okay, we can start. So the last talk is the interactive bit vector reasoning using verified bit blastering by the Henrik Böving from the Lyon Focus Research Organization.
Thanks. Hi everyone, I'm Henrik Böving. I work for the Lyon FRO and as a master student at LMU, and I'm going to present joint work with the University of Cambridge, Stanford, CMU, and ENS Lyon on interactive bit vector reasoning. So first of all, why do we care about this? Well, historically, bit vectors are a highly successful domain in automated reasoning. When people want to verify low-level programs in C or in assembly or do hardware verification, they often reach either directly for SMT solvers that are capable of bit vector reasoning, or for higher level tools like model checkers that then reduce to these bit vector logics under the hood. However, these highly automated tools often suffer from proof instability issues where when you do slight refactorings to your code or things like that, heuristics might be misguided and then suddenly proofs get slower, start timing out, etc. So for this reason, we advocate for people to use interactive theorem provers such as Lyon to give the users more control over their proof scripts so they are more stable under changes. However, we sometimes still encounter combinatorial problems where it's just too annoying to do interactive verification. So for example, here we have two implementations of a random number generator, and the second one is doing some microarchitectural tricks to get some speed ups, and we might want to verify that these two are the same for security reasons. But I mean, we could try to think about why exactly the modulo operation is equivalent to this fancy stuff, or we could just ask an SMT solver and it's going to say, yes, they are equivalent in a second, and then we are happy. And this is exactly the kind of capability that our work brings to the Lyon ITP with a new tactic called BV-decide. And BV-decide basically takes an arbitrary goal in Lyon about fixed width bit vectors, and then it applies a pipeline very similar to the current top solver in this area called Bitwuzla, where first we run a normal proof by contradiction, and then a large set of rewrite rules, approximately 200 ones, on our new goal state to simplify it, and these rules are really important to get good performance in practice. Then we reduce the conjunction of all of our assumptions into a circuit called end-inverter graphs, reduce that to a CNF, and then hand this off to a SAT solver. And the SAT solver can then do two things. It can either say, okay, there's a model for your assumptions, in which case we cannot derive a contradiction and we can recover a counterexample back to the user, or it can say there is no model, and then this is where we leave the Bitwuzla part. It can also provide us a proof that there is no model, and then we can replay this proof into Lyon to convince Lyon that indeed there is no model, so there must be a contradiction here. As we are working in Lyon, all of the steps that are marked in blue in this diagram need to have a correctness proof on their own. Unfortunately, I don't have time to go about the design of all of these components, so I'm going to focus on the first two, as I think those are the most interesting for other work. To verify all of these rewrite rules, we need to do a lot of arbitrary with bit vector reasoning, because of course we want to apply them in any kind of situation. So the first thing we did is do a lot of bit vector library engineering. And we did this using a similar approach to other components in the Lyon standard library, where we first write out all operations that we care about. So in our case, every operation from SMT-LIB's bit vector logic plus a few additional custom ones. And then we think about what ways are there to extract information from the results of these operations. So for example, we could try to interpret the result of an addition as a NUT, as an int, or think of it as a bit vector, so an array of booleans in LSB or MSB order. And for each of these interactions, we have a theorem that describes what happens, plus more creative theorems, such as algebraic properties, properties relating the different operations to each other, and so on. So we now have this very complete standard library for bit vectors in Lyon that we then used to verify all of these hundreds of rewrites rules that we got from Bitwuzla. And of course, also the reduction to circuits. But to reduce to circuits, we need a definition of circuits in Lyon. And in particular, as we are executing this definition with potentially hundreds of thousands of nodes, it also needs to be quite fast. And the circuits we're using are so-called AND inverter graphs, which is a very simple model where basically you have inputs, and then all of the logic gates are AND gates, and then depending on the color here, there either is an inverter on the fan-in or to the AND gate, or there isn't. And the way we encode these circuits is we have this Deckel data type, which can be a constant, an input, or a gate. And unlike you might expect, the Deckel gate does not recursively contain other declarations. And this is because we need to do sub-circuit sharing to avoid exponential overhead. So instead, the natural numbers here are indices into this array of declarations that the AIG is carrying around with itself. So we basically have a memory arena, and these left and right natural numbers are pointers into this arena, if you wish. So for example, here the third gate says my left input is the thing at index 0, and then that's this guy. In addition, when we're building up the circuit, we also need to be able to tell when there is a shared subcircuit somewhere. So that's what this cache is for, and this cache is built on top of the hash map from Lean standard library, which already has previously a similarly complete API, so we can just reuse that component without doing any theory on our own. And notably, both the array and the hash map have the same asymptotics as they would in C++ because of Lean's functional but in place optimization. So array behaves like a std vector, basically. And then on top of this definition, we build a framework for reasoning about functions that build up these AIGs, which unfortunately I don't have enough time to go into, and then also the remainder of the pipeline with the CNF reduction and the LRAD proof checking. Now, as all SMT solvers, which we basically are now, we care a lot about performance. So we did an evaluation on 2 data sets. The first one we mined from LVM's inst combine pass, which is about 8,000 problems, and then compared BBD size performance against the previously mentioned top solver written in C++, Bitwuzla. And as we can see, we barely have any performance difference here, apart from a few problems towards the end, which is an encouraging first result. So then we went further and took all 46,000 problems of bitvector logic in SMT-LIB, and we compared it on BBD side as well. And we took in a third tool called CoqQFPV. CoqQFPV is also a verified SMT solver, but it has no ability to interact with Coq. So it's written in Rock and Isabelle, and then extracted out into OCaml, and it runs as a separate binary. It's no tactic or anything like that. It's a normal SMT solver, if you wish. And we managed to outperform CoqQFPV by a few thousand problems. But unfortunately, unlike the previous graph, there's quite a bit of gap between BBD side and Bitwuzla here. And the main reason for this gap is that in SMT-LIB, there's a lot of problems generated from model checkers that just translate a large C program over into bitvector logic. And the bottleneck in BBD side then is the rewriting. So once we are past rewriting, everything is as fast as we could hope for. But for rewriting, we're currently using the built-in simplifier in Lean, which has a lot of additional features like unification, higher order rewriting, and so on, which can't keep up with Bitwuzla's specialized rewriter at the moment, basically. So we eventually plan to close this gap by implementing a more specialized rewriter. And as a last step on top of all this, we implemented a deeper integration with Lean's type system, where, as a little example here, we have an elevator state machine which has a current floor it's on, and a low and high floor that it may go to, and then a direction it's currently stepping towards. And these floors are also not directly encoded as bit vectors. They are wrappers around bit vectors, UN16s. Then we have the step function, which bounces the elevator back and forth between the lowest and the highest floor, step by step, basically. And here we're doing a lot of things that are not directly bit vector related. So we branch over this enum with pattern matching, we project values out, update values, we do arithmetic with the UN16s. And then we can prove a very simple invariant about this, which just says we always stay between the low and the high floor by just doing induction over the amount of steps that we take here, and then unfolding the repeat and in function or definition, and running BBD side. So all of these funky operations here, all of the branching, etc., is happening in the SAT solver. There's no case splitting in Lean, so we basically have support for a simple C-like fragment natively in BVDecide, a simple C-like fragment of Lean. So in summary, Lean now has a high-performance bitblasting tactic, and in addition to that, also a large bit vector theory in its standard library and a performant AIG library in theory that we hope will be useful for all kinds of future work that relates to bit vector theory in Lean. Thanks for your attention.
We have plenty of time for the ask questions, so yeah, please come here to ask questions.
Hey, great talk. I just have a simple question. I just wonder if the BVDecide can support some variable length big vectors. So if it is supporting some kind of concatenation or split operations and correctness for that.
So the length needs to be known. So you can do concatenation of known length bit vectors without issues. If you want to do arbitrary width reasoning, so with a symbolic width, my collaborators here are the right people to talk to. They are currently working on this. And
glad to hear that.
Yes.
Thank you.
Do you have more questions?
Hi, thanks for your talk. I was wondering, since it's like so close in performance to Bitwuzla, could you imagine using this as just a general purpose bit vector library for like just outside of Lean, just for general problems, or is there something about it that makes it better suited for Lean than for just general purpose applications?
You can do that. The question is whether you want to really. So oftentimes SMT solvers are just used to get SAT results, of course, and then you don't care if it's verified because you can just check the SAT result yourself. If you're interested in unsat results and you want to be really sure that these unsat results are correct, then BVDecide might be interesting for you as a general purpose SMT solver. And we have that wrapper on GitHub already. We used it to build this evaluation here. Yeah.
Thank you.
It's on Bitwuzla is the name. Yeah.
Hi, thanks for the interesting talk. My question is about, so your performance are run on the verified SAT solver, so do you still need to produce some kind of certification for the models?
No, the SAT solver is not modified. So we are using Cadical, and Cadical just has natively the capability to output these proofs. Basically, these error proofs here are just a trace of the CDCL algorithm, and it's just outputting its conflict clauses and how it arrived at these conflict clauses.
So there's no extra overhead for producing?
No, there's actually a paper called Faster LRAD Generation Than Checking from the Cadical people. So producing this LRAD proof is faster than even verifying it's correct. Yeah.
Thank you.
Okay. So this will be the end of this session, and yeah, thanks to the speakers again, and yeah, thanks again.